Okay, so welcome to week 6. You're half done with the course at this point, so give yourself a pat on the back. Today we're going to be talking about Paxos a lot more. Before we dig into that though, I want to talk a little bit about what the next few weeks will hold. So here's our schedule. Okay, so today is the 4th. Um, the assignment, the programming assignment that came out last Friday is programming assignment 3. So those of you who were actually in the course as opposed to just watching on Twitch, uh, if you haven't taken a look at the spec for assignment 3 yet, be sure to get started early. You have 3 weeks to do this one, but those 3 weeks are going to go by fast. For one thing, this is a tough assignment. And for another thing, you have some other things to be doing during these 3 weeks as well. In addition to the rest of the responsibilities in your life, you have other things to do for this class. So we have a couple of upcoming reading assignments. For next Monday, a week from today, we have a reading assignment. I'm asking you to read the Dynamo paper. So this is a distributed systems paper, came out in 2007, kind of a modern classic. And we're going to be discussing it in class and hitting the highlights, but you should also read it yourself as preparation for class next Monday. And then for the Monday after that, we have another reading assignment, the MapReduce paper, another modern classic of distributed systems from the 2000s. And so that's, again, we're going to be discussing the highlights in class, but you should read it for class on Monday the 18th. So these are both conference length papers, so they'll take a little time to do. So be sure to allocate time for that in between working on assignment 3. Assignment 3 is going to be due on the 22nd. Right now this is scheduled as a hack day, which was something that was very popular last quarter. So I don't plan to lecture that day. So, and this is intended to give you a little bit more time to work on the assignment. But we'll see how things go, and if I can't get through all the material in the preceding lectures, then I might have to leak over a little bit onto that day, so we'll see what happens there. I also want to share with you that we have a couple of exciting guest speakers coming up. So we have for one thing, we have a panel of recent graduates of this course. Emma Gomish, Lawrence Lawson, Victoria Tran, and Pete Wilcox are all going to be, so they all graduated from UCSC last year. And took this course at some point during their undergrad. Some of them were also course staff for me last year when I taught this course. And they're going to be coming back to talk about their experiences working with distributed systems in their time since graduation. And then we have a couple of other guest speakers on Wednesday, the 27th. Chris Callahan is going to come talk to us. So Chris is a former Googler who also ran his own online course on distributed systems, a free online course, which you can check out at distributedsystemscourse.com. It's a much more practice-oriented course than this one is. This one is more theoretically oriented. So if that's what you're interested in, go take a look at it. So Chris, actually, I found out about Chris because he recorded a brief advertisement for this course on his YouTube channel. And that drove a lot of traffic to this course. So I asked him if he in turn would be willing to come talk to us. I think right now he's going to talk about blockchain consensus, but the topic is not set in stone yet, so we'll see. So that'll be very exciting. And then our other guest speaker is Carissa McKelvey. She's a good friend of mine, has worked on a variety of interesting things, and she works for a really cool organization called Digital Democracy. I think she's going to be talking about peer-to-peer systems. And I'm excited about that because that's a topic that's very interesting and important, but we don't really have time for in the rest of the course. So she's much more of an expert on peer-to-peer systems, I think, than I am. So she's a great person to have talk about that. So that's what we have coming up. Somebody's asking on Slack, why are there ads now on Twitch? I don't know. So I do not want to subject you to ads. So this is why you have options for how you watch the course if you're enrolled in the course. You can watch on Zoom or you can watch on Twitch. They both have advantages or disadvantages, but I mean, it's possible that it's showing you ads because um, because I'm now a Twitch affiliate, but I didn't press a button that said show ads, so I have no idea. And I certainly don't get paid for those ads. All right, so the other thing I want to do before I move on to talk about Paxos some more is, so the exam, as you know, the exam was last Wednesday. We're gradually grading the exam. We're not done grading it yet. We hope to be done with grading it by Wednesday this week. So the way that we're grading it is that the course staff is splitting up the work, but a single person is doing all the grading of a given question. So it's not like we have some of the exams done and other exams not done. Rather, each exam is partway graded for the questions that we've graded so far. Much like MapReduce, actually, when you think about it. It's with the looking at the exam already that I've done, is that I've realized that there are a couple of questions that people really struggled with, and I want to talk about those. So the Chandi-Lamport question. So let's talk about this briefly. So this was a question where we showed you this run of a buggy implementation of the Chandi-Lamport snapshot algorithm. And the question was, what was the bug in the implementation of the algorithm, and what went wrong as a result of that bug? So we gave you some hints here. So we told you, so the solid lines here are application messages. The dotted lines are the marker messages sent by the algorithm. The ovals are the snapshots of the process's state, and and process 2 was the initiator. So at the point where this snapshot was taken on process 2, only event E had happened. Process 2 sent its marker message out. The marker message got to process 1. Process 1 snapshotted its state when it got the marker message. And then it sent a marker message back to process 2. Those are the only two processes participating, so there was nobody else to send marker messages to. And that was it. So what was the mistake here? What went wrong? Well, if you look at the marker message that got sent from process 2 to process 1, notice how that marker message crosses over the message that goes from event F to event D. So recall that with Chandi-Lamport, a property that has to be true, or an assumption rather, that the Chandi-Lamport algorithm makes, an assumption that the algorithm makes is that channels are going to have FIFO behavior. So that assumption of FIFO behavior is being violated here in that marker message that's going from P2. So as a result of this, notice that the marker message arrives on P1 after event D here. So many of you identified that event D shouldn't be in the snapshot, right? You noted that it's a problem that event D is in the snapshot because event F over here is not in the snapshot, and it's not okay to have an event in the snapshot if something that happened before it was there. But some of you interpreted this as meaning, well, F should be in the snapshot. So indeed, it would have been a correct snapshot had F been in the snapshot, but also the snapshot was initiated up here before F. So it's okay that F is not in the snapshot. And the problem is not really that F was not in the snapshot. The problem was that D was. So this marker message here should have landed up here before event D, and the snapshot of P1 should have been taken there. So part of the question was identifying that there was a FIFO violation here, which violates an assumption that Chandi-Lamport makes. That was the mistake that I made in my implementation of this algorithm. So the premise here was that I made a mistake in implementing this algorithm. Okay, so then why is it such a problem that event D is included in this snapshot? Well, so some of you mentioned that D was in the snapshot, but you didn't mention why that was a problem. The reason why it's a problem is because for a snapshot to correspond to what's called a consistent cut, it needs to be the case that for every event that's in the snapshot, every event that happened before it is also in the snapshot. And that's being violated if we include D in the snapshot here. Because event F is not in the snapshot, while D is. So yeah, so part of the problem was identifying the violation of FIFO. Part of the problem was noting that because FIFO was violated, this event D was included in the snapshot when it shouldn't have been. And part of the problem was explaining why it was a problem to include D in the snapshot, in particular because that made the snapshot not correspond to a consistent cut. So that was what we were looking for there. Very few people got all three parts of that. A lot of people got one or two parts of that, and so I gave a great deal of partial credit on this one. So that's what we were looking for on that one. After we finish grading the exam, I'll have a chance to talk a little bit more about other questions that people may have struggled with. So I'll have to save that for Wednesday because we're not done grading the exam yet. All right. And feel free to come talk to me if you have questions about this. Okay. So let's go on to the main topic for today, which is we're coming back to Paxos. So in lecture on Friday, we began to talk about Paxos, and this is the picture that we ended up with at the end of Friday. So this is sort of like this is like Paxos, the easy parts. And today we're going to be talking about Paxos, the interesting parts. So this is a very simple run of Paxos. We had one proposer. We have 3 acceptors and 2 learners. And the way that it worked was our proposer started out by sending this prepare message to a majority of acceptors. By the way, so there are 3 acceptors here. So a majority would be 2, but 3 is also a majority of 3, right? So any majority will do. And it would have been fine for P1 to send this message to all of the acceptors as well. In which case, they would hopefully all respond with a promise. Now, P1 only has to send it to a majority of acceptors for the algorithm to be correct. But it might be pretty smart for process 1 to actually send the message to all 3 of the acceptors in the hope that even if a message gets lost, it'll still get to a majority of them, right? Likewise, when P1 hears back from the acceptors with these promise messages, it doesn't have to hear from all of them. It only has to hear from a majority of them. So if it does hear back from all 3 of them, fine, no problem. As soon as it hears from a majority, it's happy. So it'll be satisfied as soon as it hears from a majority, but if it hears from all of them, that's not an issue. So it might be a good idea for P1 to actually send the prepare message to all the acceptors in the hope that even if a message gets lost somewhere, either on the way to the acceptors or on the way back from the acceptors, we're still going to get a majority. And if it ends up being more than a majority, no problem. Or if it ends up being more than the smallest majority, no problem. Likewise here. So what happens here? Well, we send this message out with a proposal number, which is both unique and higher than any proposal number that we've used before. We get a response back from all of the acceptors with that proposal number. Now we can send a message that actually has this value that we're proposing, which is distinct from the proposal number. So we send an accept message. Again, we have to send it to a majority of acceptors. So here I only sent it to 2, but I could have, again, sent it to all 3. And then it would have also been fine had this third one sent back. The accepted message. So when I speak of a majority, do understand that that means any majority. It could be everyone, or it could be the smallest majority, or it could be anything in between. So if there were 5 acceptors, then it would have been okay to have 3, 4, or 5. So that's one thing that one subtlety that I didn't discuss last time. There were some other subtleties that I also skipped over. So we left two asterisks, two big asterisks in our description of the algorithm, if you remember. And what we do in those cases is actually more subtle than what we talked about last time. So we're going to go through the whole thing again today, filling in the asterisks. And with them filled in, hopefully we'll then be able to look at some more interesting runs of Paxos, including runs that have more than one proposer. And I hope that this will also lead us into a discussion of why Paxos is not guaranteed to terminate. Okay, so one thing that I want to point out here, which we started to talk about last time, is that there are several milestones in a run of Paxos. So let's try to identify what those milestones are. Somebody just asked in chat, did she just draw an acceptor sending a message to other acceptors? So, okay, I have two questions here. One, why do you all talk about me in the third person? Why don't you just ask, did you just draw? But the answer to the question is no. There's no place where an acceptor is sending a message to other acceptors. Okay, so what are the milestones in this run of Paxos? So the first milestone, yeah, right. So there's a lot of lines in this picture. I know it's hard. It's going to get worse. So we'll do our best. If there were any point when I wished that I had more than one little 8.5 by 11 sheet of paper to teach this course online, it's when teaching Paxos. So these diagrams are going to get messy, and I wish I had a gigantic blackboard to draw them on. All right, so let's look at what the milestones are. The first milestone comes when a majority of acceptors have promised a particular proposal number. So that milestone in this picture happens right here. I'll call it M1, milestone 1. So milestone 1 is a majority of acceptors have promised a particular proposal number. So a promise of n means I'll ignore any request with a promise, or excuse me, I will ignore any request with a proposal number lower than n. So in particular, this means that the acceptors are never going to accept a proposal numbered less than n. That's milestone 1. The second milestone is this point right here, where we said consensus is reached. And that happens when a majority of acceptors send this accepted message for a particular proposal number n and a particular value. At that point, consensus has been reached even though nobody knows it yet. So that's the point of no return. Other things may happen in the algorithm. Somebody else might even propose something else. But no matter what, at that point, sooner or later, that 0 is going to be what you end up having consensus on. It might take a while, but you'll get there. And then finally, we said there's a third milestone, which sort of happens individually for every proposer or learner. So the third milestone is when a proposer or learner gets an accepted message from a majority of acceptors for a particular n, that's when they know consensus has been reached on the value. So this right here is milestone 3 for the proposer 1, because right here is when they've gotten those accepted messages from a majority. Learner 1 got them here. Learner 2 got them here. So that's milestone 3, the point at which these participants in the algorithm know that consensus has been reached. So those are the milestones. Milestone 1, a majority of acceptors have promised a particular proposal number. Milestone 2, consensus has been reached. Milestone 3, individual participants know that consensus has been reached. Okay, so that's Paxos, that's easy mode Paxos. We're going to write out in detail the steps of the algorithm with the asterisks that we put in last time, and then we're going to fill in what goes in place of those asterisks. Okay. So a run of Paxos starts with a proposer. So we say, when a proposer wants to propose a value, it sends prepare n to a majority and recall that this could be the smallest majority, or it could be all of them, or it could be anything in between. So n has to be unique. So nobody else can send that particular proposal number. It must be unique. And furthermore, it has to be higher than anything that particular proposer has tried before. Notice I say it has to be higher than any proposal number that proposer has tried before. It doesn't necessarily have to be higher than any proposal number in the whole system, which is good, because if it did have to be higher than any proposal number in the whole system, that would be an enormous pain in the ass, right? Because you would have to go around to everybody and find out, oh, what was the last proposal number that you used? Okay, don't use any more. I'm going to use the next higher one. So that, in a distributed system, that would be miserable. And it's a good thing we don't have to do that. Instead, it's just this local property. It just has to be higher than any proposal number that particular proposer has tried before. So if P1 sends prepare 5, if there were another proposer over here, it would be perfectly fine for that proposer to send prepare 4 at that point. It might not have much luck doing so, because by the time that prepare 4 message gets over here, these acceptors might have already promised 5, which would mean that they would ignore the prepare 4. But there's nothing that says that proposer 2, if there were a proposer 2 here, couldn't send a prepare 4. Okay, so that's what the proposer does initially. Then we go over to the acceptor. When an acceptor gets this prepare n message, it asks, did I previously promise to ignore requests with this proposal number? So it asks, did I promise to ignore requests with this proposal number? If the answer is yes, then it ignores it. If no, it replies to proposer with promise n, which means I promise to ignore requests with a proposal number lower than n. This was our first asterisk. So we'll come back to that. For now, let's go back over to the proposer. So we've seen the initial message from the proposer to the acceptors. We've seen what happens when the acceptor gets one of those and replies with promise n. Back over to the proposer. So we'll say, when a proposer has received promise messages from a majority of acceptors, for a particular n, it sends an accept message to a majority of acceptors with that n. And where val is the value that it wants to propose. This was our other asterisk. So we'll have to come back to that as well. And then finally back to the acceptor again. So when the acceptor gets one of these accept and val messages, it asks, did I previously promise to ignore requests with this proposal number? And if yes, it ignores it. If no, it replies with accepted of the proposal number and the value, and sends that to all the learners as well. So it's this four-stage thing, right? Back to our first picture. We've got messages bouncing back and forth between the proposer and the acceptors. So this is, we could number these if we want to. 1, 2, and then here's the other page. 3, 4. So we left 2 asterisks in here. To understand why we need to add something more to this algorithm, let's take a look at what would happen if we had more than one proposer. So we'll draw this picture, but just to make it a little bit easier to read, let's leave out the learners. We'll pretend they're there, but getting rid of them won't mess up anything in this example, and it'll make it a little bit easier for us to draw. Okay, so let's say that we have a proposer and 3 acceptors, just like before, and another proposer. Okay, so let's talk about what would happen in a few situations here. So let's say, again, let's say that proposer 1 sent out a prepare message with proposal number 5. And we'll say that we got the promises in response. And we'll say that our accept messages went out here. Let's say the value that we're trying to get consensus on now is 1. So I haven't drawn any messages to learners, but imagine that they were there. Okay, so first of all, what would happen if proposer 2 sent a prepare for message to the 2 acceptors? And let's say that it lands right there. Maybe it sent it to this one too, it doesn't really matter. Okay, so what happens on those acceptors when it gets that prepare for message? Anyone want to tell me? Yeah, so somebody said reply with promise for. So let's take a look at what the rules for the acceptor are. So we say when an acceptor receives a prepare in, if it previously promised to ignore requests with that proposal number, it ignores it. So did it make that promise? Well, that's what this promise message means right here. Maybe I should fill this in here. So when the acceptor replies to the proposer with promise N, what that means is I promise to ignore requests. with a proposal number lower than n. That's what promise n means. So going back to our picture, at the point when this prepare for message hits acceptor 1, it's already sent promise 5, which meant it's already promised to ignore requests with a proposal number lower than 5. So it's just going to ignore this prepare for message. Same thing for acceptor 2. It's already made a promise to ignore any request with a proposal number lower than 5. So when it gets the prepare for, it'll just ignore it. It won't crash the system or anything like that. It'll just ignore it. Now maybe A3 over here will send back a promise for, because maybe A3 hasn't heard from anybody yet. But there's no way that P2 is going to hear back from a majority of acceptors, because even if it hears back from A3 with a promise, it's not going to hear back from these two. So it's not going to hear back from a majority if a majority have already promised a higher proposal number. So it'll sit here waiting. P2 will sit here waiting to hear from a majority of acceptors, and it won't. So eventually it'll time out. All right, so keep in mind that process 2 or proposer 2 has no idea what's going on with proposer 1 over here. All it knows is that it sent a prepare for and that it only heard back from one acceptor. It doesn't know why, right? It doesn't know if that's because these acceptors over here are just slow or what. It doesn't know that there was necessarily this other thing being promised. So what can it do? Well, it turns out that it's okay, always okay, to just go ahead and send a higher numbered prepare message. As long as the proposal number is unique, you're okay. So here, I'm assuming that P1 has to send odd numbered proposals and that P2 has to send even numbered proposals. But you could use any sort of scheme for this as long as it ensures uniqueness. Okay, so P2's over here waiting to get promise for messages from a majority of acceptors, and maybe it gets one from acceptor 3 if it happened to send to acceptor 3, but it doesn't get the majority that it needs in order to do anything. So in practice, the way that this would work is that the proposer has some kind of a timeout. If it sends a prepare message and enough time goes by and it never hears from a majority of acceptors, then it can send a higher numbered one. So let's say that after a while, P2's timeout expires and it decides to send a new prepare message, prepare 6. So this prepare 6 message goes out to, let's say, all the acceptors. So what happens now? Have any of them promised to ignore requests with a proposal number of 6? Sorry, this prepare 6, this should have gone here. Have any of these acceptors promised to ignore requests with a proposal number of 6? No. So they have to respond. But this is where that asterisk comes in, right? We've already hit our second milestone in our Paxos run. So right here, was milestone 2, right? This point at which a majority of acceptors sent these accept messages with a particular proposal number and a particular value. So consensus has been reached. It's just that P2 didn't know it yet. P2 is still out there trying to send new proposal numbers. So the acceptors are now obligated to tell process 2 over here that they already accepted a value. So we have to add something additional to what we wrote down before. So here's what we said before. When the acceptor receives a prepare end message, if it previously promised to ignore requests with a proposal number, if yes, it ignores it. If no, we said it replies to the proposer with promise n. But this is the case that we have to fix, because this is the case where the acceptors have already actually sent those accepted messages. So instead of just replying to the proposer with promise n, we have to add something else in here. Right here. It asks, have I previously accepted anything? If the answer is no, it hasn't previously accepted anything, then what we wrote up here is still true. It replies to the proposer with promise n. So this is the arrow that we follow. I guess we go back up here in case if the answer to that is no. But if the answer is yes, it has previously accepted something, then it has to tell the proposer that somehow. So it has to respond to the proposer with a promise message, but that promise message has to tell it what its highest previously accepted proposal number and its previously accepted proposal value were. So it puts something extra in the promise message. So it still does a promise of n, but then there's this extra piece in the promise message where it's a pair. I'm going to call it n previous and val previous. Where n previous is its highest previously accepted proposal number, and val previous is the previously accepted proposal value. So this promise message now has two pieces. There's the n, which was what it got in the prepare, and then there's the previously accepted proposal number and the value that went with that accepted thing. So a promise message only has this additional component that only gets used if the acceptor has previously accepted something. So let's see how this looks in our picture. So here was this prepare for request. This one times out. This new one gets sent. So A3, what does A3 respond with? Well, A3 hasn't accepted anything, right? So A3 can just respond with promise 6 right here. There's nothing stopping it from doing that. What about A1 and A2? Well, they can respond with a promise message, but it has to have that additional component. So their messages are going to look like this. Promise 6, and then that extra piece is going to look like 5-1. All right, I want to go back and look at some of the messages that are, or some of the questions being asked in chat. So one question was, what happens if duplicate prepare end messages are received at an acceptor? Yeah, okay, so maybe, so do you mean from a given proposer? Yeah, so if 2 instances of prepare 5 came here, then yeah, that proposer, and I guess it depends how it's implemented, right? If that acceptor knows how to do some sort of deduplication, then maybe it would only send back 1 promise. In any case, it doesn't matter if multiple promises of the same proposal number come back from the same acceptor, because 3 or 4 or 5 is as good as 1. P1 is waiting to hear back from a majority of acceptors. So it's not the message count that it's waiting for. It's waiting for them to come back from distinct acceptors. And there's another question. What happens when a prepare n+1 is received before the accept has been handled? Okay, so the question was, what if this prepare 6 message, let's say, landed up here? What if that had happened? What if proposer 2 had sent an accept, or excuse me, what if proposer 2 had sent a prepare 6 message and it landed up here on acceptor 1? Acceptor 1 had already promised 5. Well, which case is that? You can look at what we wrote down. When it receives a prepare end, did I previously promise to ignore requests with this proposal number? No, it didn't. Then we go here. So, have I previously accepted anything? No, it hasn't. So we go back to this case. It just replies with promise n. So yeah, if that were to happen, if the prepare 6 message had hit here, then A1 would then reply with promise 6. And then you're probably correctly anticipating one of the things that could go wrong here. Then when P1 tries to send these accept messages, they're going to get ignored. So if you're starting to wonder if this causes, if this could cause a case where Paxos doesn't terminate, you're right. Okay, so before, oh, by the way, let's see. Okay. Sorry, I get a little confused when I'm teaching Paxos sometimes. Okay, so in this case here, now P2 has gotten promise messages from everybody for its proposal number 6, right? But only one of them is promise 6, and the other 2 have this extra information tagging along, which says, okay, I promised 6, but by the way, I already accepted proposal number 5 with the value of 1. So presumably we did that for some reason, right? We're sending that information to P2 because we want P2 to do something with it. So that brings us to our other gap that we need to fill in the algorithm, our other asterisk. So let's look at what the proposer is supposed to do when it gets those promise messages. So that's this part of our algorithm. So before we said that when a proposer has received promise messages from a majority of acceptors for a particular n, it's going to send out this accept n message with the value that it wants to propose. How do you think that we're going to have to tweak this part of the protocol? So here again is our picture of our example run here. And this is the situation that we're in, where proposer 2 has sent out this prepare 6, and it's gotten one promise 6, and then 2 promise 6s that have this extra information tagging along. So what do you think that the proposer is going to have to do with that information? Somebody just asked, how does an acceptor know that P2 doesn't know about the reached consensus? Well, how do the acceptors know that P2 doesn't know about the reached consensus? Well, and presumably if P2 knew, then it wouldn't be sending out this prepare message to propose something new, right? But if it does know, it's not a problem to tell it again. Okay. So the proposer, P2 here, is going to have to take into account somehow this extra information that was included in these promise messages. In particular, what it has to do is look at these pairs of a previous proposal number and a previous value. It's going to look at whichever proposal number is the highest. And then, when it does a proposal later on, the value that it must propose has to be the value that went with that highest previous proposal number. So in this case, they both happen to be the same, right? They both happen to be 5. So essentially, we're saying here, okay, P2, you can propose a value, but it has to be the value that went with this previously higher accepted proposal number that we've just told you about. I find this funny, actually. This is an aspect of Paxos that I think it's funny. It's like, oh, okay, like you can go ahead and issue your own proposal with your own proposal number if it makes you feel better, but you have to propose the thing that was accepted before. Okay, so we're going to revise the protocol that the proposer follows right here, where these 2 asterisks are, as follows. So we said, when a proposer has received promise messages from a majority of acceptors for a particular n, it sends this accept message to a majority of acceptors with that particular n, and where val is not necessarily the value it wants, but where val is chosen as follows. if the proposer has gotten any of these pairs, it has to pick the value that went with the highest previous proposal number. If it hasn't previously gotten any of these n-prev, val-prev pairs, then it can pick anything it wants. So in our picture, we're running out of room here, so let's kind of zoom in on this bottom right of the picture here. Let's say we have a scenario like this. So we have A1, A2, A3, and P2. There was some previous stuff that went on these processes, which we won't draw. So P2 sent its prepare 6. It got back a promise 6 from A3, and it got back promise 6, 5, 1 from A2 and A1. Okay, so P2 can now send an accept message out, and it can send to every acceptor, but it only has to send to a majority. So let's say it sends to A2 and A3. And it's required to use this value 1, because that's what it was told was previously accepted. So it's sending its accept message out with proposal number 6, because that's the proposal number that it was planning to use all along. But it has to, now that it's actually proposing a value, the value it has to propose is 1, because it was told that that was what was previously accepted. So it's still using its own proposal number. Note that it didn't have to change its proposal number to 5 or anything. It's sticking with its 6. It just had to make sure that the value it's proposing now is the one that it heard about. Okay, so what do the acceptors do? Well, what does an acceptor do when it gets an accept message? What do our rules say? When an acceptor gets an accept message, it asks, did I promise to ignore this? Well, did our acceptors previously promise to ignore messages with a proposal number of 6? No, they didn't. All their interactions with P1 over here had a proposal number of 5. So it didn't previously promise to ignore things with a proposal number of 6. So it doesn't have to ignore anything. Instead, it can reply and accept. But, well, it checks to see if it previously promised to ignore requests with that proposal number. It did not. So it replies. So notice that A3 and A2 have the same behavior here. Even though A2 we're saying had these earlier interactions with P1 and A3 didn't. Okay. So notice that this doesn't do anything to invalidate the earlier consensus that was reached on the value of 1. It has a higher proposal number, but the value is the same. So that's why we had to add this extra subtlety to the behavior of the proposers and the acceptors, because we needed to make sure that a previously accepted value got repeated and reinforced. So A3, for all it knows, it never saw any of these other promise messages over here. As far as A3 knows, this value of 1 was P2's idea all along. So A3 doesn't know that this value of 1 came from originally from P1 over here, but that's okay. All right, questions about this? So this is very complicated, right? And in fact, we're almost out of time. And I didn't even have time to do the quiz question today. So in the couple of minutes that we have remaining, I'm going to switch over and do today's quiz question. And I didn't even have time to start to talk about some of the other interesting aspects of Paxos. So we'll do those next time. But let's do our quiz. So here's today's quiz question. And I'll leave that open for a few minutes after lecture officially ends. So there was a question on Twitch. What happens if the accepted values are not the same? So you're gonna have to, okay. So let's say that, let's say that P1 is interacting with A1 and A2, and let's say that there's another proposer over here. Well, if A1 and A2 both accept for a particular value, and then another proposer over here gets to the point where it's sending accept messages. So keep in mind, it has to go through the sequence of prepare and promise first. So if it's then sending accept messages, Well, if a value over here has already been accepted, then it's not going to be able to hear back from a majority if it's trying to get a different value accepted. So I urge you to go and try to take the rules that I wrote down and try to demonstrate the issue that you're imagining, um, and basically try to break the algorithm. I don't think you're going to be able to. All right, we're out of time for today. I'm going to leave the quiz open after lecture is officially over because I opened it up so late. Sorry about that. But we're done for today. And we're going to come back next time and talk about other aspects of Paxos. And hopefully we're going to get to that question that we started to anticipate today, which is situations where this algorithm doesn't terminate. So see you on Wednesday.